Hello, this is our MAE 152 final project. We are Group 7 with Brandon, Rachel, Ryan, and Tomas. We analyze an upright, chassis, control arm, and brake rotor.
The upright is a critical structural component that connects the suspension to the wheel assembly, housing the wheel bearings and suspension mounting points. The material used is 6061 aluminum at T6 condition with a yield strength of 39,885 psi. Two static loading cases were performed, the first being max bump simulating peak forces experienced during suspension compression, and the second being a thrust load, simulating lateral forces during cornering. Modal analysis was also performed to analyze natural frequency. The first simulation applies 6 loads, 5 of those being lateral loads from the suspension linkages shown in the table and 1 from the braking force. The second simulation uses a few assumptions and simplifies a cornering scenario into a statics problem in order to estimate the relative vertical and lateral loads. Some key issues identified in the original design were high stress values in the max bump case. The displacement could also be reduced to prevent excessive bending as well as the need to improve structural stiffness. So two design iterations were made. The first iteration adds reinforced vertical extrusions to reduce the joint stress concentrations, and a second iteration uses a cross brace in the pockets. The iterations also show the mesh used for the following simulations. Under max bump, both iterations significantly reduce the max stress and displacement. Under the thrust loading condition, the first iteration reduced the max stress and displacement, while the second iteration experiences greater stress but a reduction in displacement. The modal analysis shows the first natural frequency mode twisted the upright along the vertical axis, where both designs improved vibrational performance. Under these loading conditions, the design variations indicate an improvement in stiffness.
Hi, my name is Rachel Koo, and for my portion of the MAE 152 project, I did analysis on the brake rotor. So the brake rotor decelerates the wheel upon braking, and it is modeled as ASTM 836 steel. So my design versions include the plain brake rotor, and then a brake rotor with increased thickness, and then a brake rotor with increased air gaps or hole sizes. My brake rotor closed form solution versus FEA solution resulted as a hand calculation max von Mises force of 14.53 MPa, and then the FEA simulation for the max braking force was 15.65, which led to a percent error of approximately 7%. The FAE summary, I decided to highlight the brake rotor increased thickness iteration. And the max braking torque from the original was around 15 MPa, and the new one was around 9 MPa, which led to a percent error of minus 66%. So a decrease in about 66%. Some of the failure modes for the brake rotor include fatigue, and this might be due to the repeated cyclic loading from braking, and shear, because those high braking forces can lead to very high shear forces at the mounting points. And then lastly, buckling, because of large compressive stresses from braking and the thermal expansion.
The chassis is the base structure that all of the vehicle's components are mounted on. 3 static loading cases were performed. 2 are presented here, where one is the front impact if the vehicle were to collide with a rigid body at 40 miles per hour, and the second case would be if another vehicle collided with ours from the back at 60 miles per hour. A third case was also conducted to analyze the vehicle's torsional rigidity to improve the handling and performance of the suspension. So the goal is to minimize the impact displacements for the safety and control of the driver. With the original chassis, it did not have any triangulating members in the front structure. Thus, the vehicle experienced high stress points at the weldments attached near the compartment of the driver. Through iteration 1, added 2 sets of triangulated members that crossed between the suspension mounts in front of the vehicle. In iteration 2, in order to increase the vehicle's overall stiffness, I increased the wall thickness of the members that are color-coded in red from 0.083 inches to 0.103 inches. Under the front impact case, the first iteration decreased both the max stress and displacement by around 14%. While the second iteration decreased both values once again around the 8% range. The additional members would distribute load more evenly across the structure while also increasing the stiffness of the vehicle. Looking at the torsional analysis, I believe that the 7th and 8th mode shapes were the most important, as it represents twisting along the long axis of the vehicle and longitudinal flexion. On the table is the 7th natural frequency, and you can see that it decreases with every iteration, meaning that the additional members and increase in thickness improve the overall torsional rigidity of the structure.
Component to the car's suspension, and these are made out of 4140 chromoly steel. We have load cases for maximum acceleration, maximum braking, and lateral force. The first design iteration, there was an increase in the outer diameter of the tubing and wall thickness, and for the second design iteration, there's an increase in the thickness that mounts the spring and damper. According to the summary table, there was a significant improvement for the first design iteration and only a slight improvement in stress for the second design iteration, and a decrease in performance for the displacement all the way around. We also performed a frequency analysis, which saw an increase in the frequency for the first design iteration and a decrease for the second design iteration. For fatigue, there's high stress points at the ends and at the joints of the control arm. We might see some crack formation at these high stress areas. The tubes are also in bending, and we can also see buckling from the lateral force. For the closed form solution, we calculated a critical load of 192,000 newtons, which is way above our calculated lateral force, and this is consistent with our FEA results.